Hi there. Can everybody hear me okay? Yes? All right. Let's talk about Bezier curves. So a Bezier curve is a way of representing a curved shape called a spline. And instead of having individual pixels that make up this curve, we do that instead with 4 control points. These control points can be used to scale this curve at any resolution. Bezier curves are an integral part of vector design in Photoshop, Illustrator, and Sketch. They're also used in automotive design, CAD design, and even to model smooth animation timing. Of course, we can use this concept of a Bezier curve in Swift with the UIBezierPath class. So we can move to our starting point, and we can add a curve to an end point flowing through 2 control points. Then we can add that path to a context and stroke it to draw our curve. But this doesn't really help our understanding of how this even works. So what are these control points? How do they influence the curve? And that's what we want to take a look at today. So to understand this, we need to understand the math behind it. This is math invented by a man named Paul de Castelgio. Despite the Bezier curve carrying the name of Pierre Bezier, Paul de Castelgio was the one who first proved the math behind the concept. And de Castelgio's algorithm is best expressed visually. It works with any number of points. You start off by connecting the points with line segments, but 2 points don't really form a curve, so that's not so interesting. Instead, we're going to add 2 control points, and we're going to pass the line segment between the control points like this. Next, we need to pick an arbitrary value we'll call t from 0 to 1. And at 0 or 0%, the value, we're going to push a point along the line segment. If we look at that first line segment on the left, we will have a point that starts at the starting point. And a t-value of 1, it'll be at the end of that line segment. So if we choose a t-value of 0.5, we can put a dot right in the middle of each line segment. That's 50% across the line. We can then take these new points and connect those with line segments. And now that we have 2 new line segments, we can again take our same t-value of 0.5 and put a dot halfway along the next line segment. Now that we have 2 new points, we can connect those with a final line. And again, using the same t-value of 0.5, we put a dot halfway along the new line segment. So this yellow dot is exactly the point of where the Bezier curve will be at 50% through drawing the curve. So let's take a look at this in an interactive way using Xcode Playgrounds with Swift. We're going to start with some boilerplate code that I've already created with a Bezier view. This is a UI view subclass that has a start point, an end point, and 2 control points. I've also attached gesture recognizers to the 2 control points so you can move them around with your finger. And we have a helper function called drawPoint that we will use to draw a point of a given size and color. So let's go into a demo. We are over here in Xcode, and you can see the view that we've created on the right-hand side. This view on the right-hand side has the start and end points defined, and they're fixed right now. And I can tap to add my 2 control points. If I toggle this switch here at the bottom, it will draw the curve with the built-in UIBezier curve, or UIBezierPath class. So we can see that by moving the control points, we can see how that affects the curve. But we don't want to use the built-in one. We want to build it ourselves to further our understanding of how it works. So we're going to start by connecting our line segments up between these points. So I'm going to scroll down to a function called drawBezierParts. And we're first going to move to the start point. Then we're going to add a line to the first control point. Then add a line to the second control point. And then add a line to the end point. Now we need to set up our line style. So we will use a light gray color to stroke the line. We will set our line width to 2. And then set this to be a dashed line with a phase of 0 and a length of 4. Finally, we can stroke the path to draw our lines. So as I add the 2 control points, you can see the line segments are being created for us. I also have a slider here at the bottom. And this slider is going to be what I call the time slider. It controls a time value from 0 to 1, and that's what we're going to use for our t. So right here, we're going to check to see if the time value is greater than 0. And we need to create points along those line segments. To do that, we need to linearly interpolate between the start point, the first point, and the second point of the line. So I'm going to scroll up to the top and create an extension on CG point to do this linear interpolation for us. It is common to shorten the phrase linear interpolation to just lerp, which is also fun to say. We're going to lerp our point with another point over that time value. And this is going to return a new CG point. So we can create the CG point with an x and y value. The x value is going to be inversely related to t for our x, and then t times the other point's x value. And the same thing for y here. 1 minus t times y plus t times other dot y. So if you just quickly check the math here, if t is 0, then the first component is 1 times x, so you get 100% of the first x value. And then for the second part, if t is 0, then you get 0% of the value from the second part. If t is 1, then the first element is zeroed out, and you get 100% of the value from the second part of the equation. So this will blend in between with a weighted average between the 2 points. So with that function, we can go back down to where we were checking our time value here, and we can create 3 new points along those line segments. So we're going to call these points T1, T2, and T3. This will be the start point, lerp, control 1, with the time value from our slider. And we're going to do the same thing for T2, which will be C1.lerp C2. And T3 will be C2.lerp C3. We can then draw these points. So I will put these in an array, call for each, and call that helper function we saw earlier, draw point. We're going to draw $0 as the point. We use the color magenta and a radius of 8. So, endpoint, thank you. Pair programming. Okay, so if I change my time slider here, you can see that these points are traveling along their respective line segments. Okay, we have 3 new points. We can use those points to connect them with new line segments. So let's follow the same pattern. We will say context.move to T1, add line to T2, add line to T3. We will set our color to magenta and stroke the path. So now we have magenta lines that are moving. Okay, so we can move on to the next step, which would be to draw a point that travels across the magenta lines. We're going to call those U1 and U2. So that's going to be T1.lerp T2. U2 will be T2.lerp T3. And then we can draw these points as well. $0 for the point. This time we'll use green as the color, 9 for the radius. Now we have these green points that are moving. Now because the green points are traveling along a line that is also moving, the green points are actually starting to curve. So you know what the next step is. We need to connect the green points with a line. So we will move to U1, add a line to U2, set our color to green, and we will stroke the path. And for our last step, we're going to add a new point we will call V1, which will be U1.lerp U2 over that time value. Then we can call draw point for that one. We'll use the context, V1 as the point, yellow for the color, and a radius of 10 to make it nice and big. Okay, so the yellow point is the point along that curve as we were drawing. So if we were to put our pencil down here at T0 and just follow the yellow point across, it would draw our curve. And we can even check our work here by overlaying the built-in UIBezierPath curve on top of that to see how that works. And we can play with these control points to see how this math produces that curve. We can go one step further if we want to actually make it look like we're drawing this curve by using a CA shape layer, giving it a Bezier path with the same control points, and we set the stroke end property of our layer to that time value. Now if we do that, it's going to stop drawing at that position in the curve. So the orange line follows exactly where our time value is. Okay, so I mentioned before that De Castelgio's algorithm works with any number of points. So we can simplify our example and allow it to work with more than just 2 control points. We're going to change our class to instead take an array of points. So we can add any number to them. We can also factor out our logic from earlier. You saw it was very formulaic. We started with 4 points, then we went to 3, then we went to 2, then we went to 1. So instead we can write 2 functions. The first one is draw lines between, and we're going to give it the context and the points. This function is going to move to the first point in the array, and for every other point in the array, using drop first returns a slice of the array that excludes the first element. We can add a line to every other element in every other point in that array. Then we set our line style and we stroke the path again. So that's one function that can take an array of points and draw the lines between them. If we have our time value greater than 0, we can interpolate between these points again with another function. Interpolate between takes the context and the points We do a quick guard to bail out if we don't have at least 2 points. So this is where we will exit this algorithm. We're going to keep an array to hold our interpolated points. Then we're going to loop over every point in the array except for the last one. And we do that because we want to make sure that we can grab the current point in the array plus the one next to it, so we can compare the two. We do our linear interpolation of these 2 points and add it to our array. Finally, we draw that point. And if we have more than 2, or at least 2 points, we can draw lines between those points. So it's the same algorithm, but this one recurses into draw lines between. And it will continue until we only have 1 point left. So we can't draw a line between 1 point. As it turns out, that code can be simplified and improved a little bit by using functional programming. Zip is a function that takes 2 sequences. Here we have a sequence with 5 items and a sequence with 4 items. And when we zip those together, we get back a new sequence of tuples with each of the elements lined up. It's important to note here that the zipped result takes the length of the shorter sequence. So our resulting array has only 4 items. And thus will never contain a nil value. So if we use our array of points as our first sequence, and we use drop first to have a second sequence with the first point excluded, now these arrays are offset by 1, and we zip those together, and what we get is a new array of tuples with each point followed by the one next to it. This is a perfect data structure we can use. So we're going to write a new function. This is a pure function called Interp zip, which will use zip to interpolate the points that we've given it. This one is going to return a function. So notice that the first statement is return with a closure that takes our t value. So we're returning a function that takes our t. We call zip on our points array with points.drop first as the second sequence, and we get back our array of pairs. We can map that, and each pair gets linearly interpolated, the first element to the second. Okay, so let's see what that looks like. So in this demo, you're not constrained to just 2 control points. I can add as many as I like. And when I drag this time slider, you get to see this very interesting effect of what a higher order curve looks like. It's also worth noting here that we no longer can draw this with UIBezierPath because we are having multiple control points. So to draw this, we have to step through each value of t all the way up to our time slider. Doing that can be quite slow depending on how much we increment t each time through the loop. As you can see, it's quite choppy. And that's because I've chosen a t value so small, or a t increment so small, that I get a smooth curve. But if I choose a larger increment, our curve will draw faster, but it will be jagged. This type of code can be optimized further by only drawing the segment of the curve that is actually changing. And by using the math behind de Castelgeo's algorithm, you can subdivide a curve into 2 different curves that follow the same principles. And you can join those curves later to create your larger curve. So by using Swift Playgrounds, we get rapid feedback on our ideas. We're able to experiment. We're able to explore. And I think this is an important concept to be able to further and strengthen your own understanding of something that you may not be familiar with already. Thank you.